All right, so welcome back. Today is November the 6th, and we're going to continue here our practice homework from chapter 9. All right, last time when we met, we were covering these topics of SN1, SN2, E1, and E2. If you don't mind, I'm going to remove this. So, excuse me, because I cannot breathe and talk at the same time with this mask. All right. So, and then we figured out that when you have a tertiary alkyl halide that has a chiral carbon, then you can have a mixture of a 50-50 mixture for the SN1. I'm going to flip my computer here. I'm gonna continue here. All right, so let me grab this. It says, describe the following chemical reactions as SN1, SN2, E1, and E2, and draw a curved arrow mechanism for each reaction. All right, what do we have here on this next slide? So here, actually, I forgot that this was tertiary alkyl halide because this carbon here has 1, 2, 3 neighbors. So it's tertiary. How about the next example? What is this? Is it an SN? Is it a substitution reaction? Yes or no? No. The moment that you see a double bond, that is an elimination. So it's an E reaction. So we cancel SN1 and SN2. And is it E1 or E2? What do you think? And why? To answer this question, you have to look at the components of the reaction. So let's take a look. So for this reaction, we have a secondary alkyl halide. Usually when there's secondary, there's a war between SN2 or E2. Also, you have a charged nucleophile. This is a charged nucleophile or base. The terms are interchanged here. Sometimes it acts as a base, sometimes it acts as a nucleophile. So, and then we have ethanol. What is ethanol? Polar protic or polar aprotic? Polar protic, because it has an OH group. All right, so it gives that H, that proton, that makes it protic. All right. This is a really, really interesting example. Because notice that this H is down and the leaving group is up. So you had to grab the H, the proton that is anti-periplanar, to the leaving group, right? We talked about last time. And so the sodium is a spectator ion. The base grabs the H and makes a double bond and kicks it out. All right. All of this, because it was charged, I can say with confidence that this is an E2 reaction. All right. If the nucleophile was neutral or weak, that would have come from an E1 reaction. All right. Because the components of the E2 are the same as the SN2. The reagents are very, very similar. The prediction is what counts, though. And the components of the E1 are the same as the SN1, all right? The reagents and the temperature. All right, let's do the next reaction. What do you think you have? Elimination or substitution? Substitution, so we start with an SN. Is it SN1 or SN2? SN2, very good. You can see that this iodine was exchanged with the, this is a thiol group, all right? So when the S has an H, it's called a thiol group. Check this out. This is a thiol. We're not going to talk too much about the thiol groups, the sulfur groups. Actually, we're going to skip them in the next chapter. because they stink. Literally, they stink, but they're really great for research. I actually use them all the time, and I had to go home and take a triple shower. So like I take like I take a shower in the morning to come to work, and then I go and take a shower after I go home, and I still take another shower before I go to bed because the sulfur will stick to your hairs, and so it stinks like fish or something like that. So it's very nasty, but they make for great drugs, and so thiols have it ends with a sh. Now, if you had like a methyl group, this becomes a mercapto group. All right. So the naming changed a little bit. All right. Okay. So also notice that that this molecule was flipped on purpose because, and this is something that you have to deal with when it comes to publishers. They always try to make the student think a little further. So just be vigilant of that. Like, notice that you started with this tether like that. So I don't know why the publisher didn't draw this. And that. But they always try to trick us a little bit. So just make sure that you know that there is inversion of configuration here, 100%, and then that you put a new group there. And this molecule is chiral. So you will have one. All right, I forgot to say that this was a secondary alkyl halide. So always do what I'm doing. I'm doing some sort of like investigative analysis. I check for my base. So this is a charged nucleophile. The moment that I have a charged nucleophile, I know SN2 or E2. All right. I check my solvent. My solvent is telling me that I have polar aprotic. It's DMSO. So polar aprotic means good for SN2. So that enhances the SN2 chances. Then I know, oh, this is definitely SN2. All right. And it's not E2 because I don't see a double bond. All right. Next example, it's pretty cool, actually. It tricked me at the beginning, but it's just the way that it's being looked at. So check this out. What do we have here? We have a charged nucleophile again. Charged nucleophile. That's a strong nucleophile. I should have write that down. Strong charged nucleophile here. I'm going to say strong charged nucleophile because the opposite is neutral weak nucleophile. All right, for the SN1. For the SN2 is strong charged nucleophile. This is OH. That's the base. It's the base, and in this case, it's going to be the nucleophile. And the MSO again is polar. It's a polar aprotic solvent. All right, check this out. When this nucleophile comes and attacks here, it's gonna kick this guy out, right? But it also, and I like being in class so I can show you with my hands what's happening. You have this carbon here is up, so it's a headrest on the share. You see that? Here's your share, right? Here's your headrest. And it went from a headrest to now a footrest. You see that? So basically, with the attack, pow, it went down. You see that? And so when that happens, these two bonds, they are pushed down with the nucleophilic attack. How cool is that? And that changes the stereochemistry of the molecule. And look at this. So if you put it like, let's say you put your eyes this way, You're looking from the back of the molecule because this is a bicycle. Now, looking at this molecule this way, this is the eyes. Now you're looking to like the front of the molecule. Do you see it? Can you visualize that? Yeah. So there are two cyclic structures here. There's a 6-member ring boat. This is a boat, and a puck cyclobutane. You see it? It's right here. This guy, this one. I'm gonna delete all that because I'm making a mess. But you still end up with your 6-member ring, and here's your puckered cyclobutane facing the other way. All right, so that is your bicyclic molecule. And so this reaction is SN1, SN2, E1 or E2. What do you think? So we cancel the E ones because there's no double bond, so this is SN2. Very good. What threw it away for SN2? What helped you? The inversion configuration. Also, a strong nucleophile. Exactly right. Those two things help. All right. And if you are listening online, you can also participate and ask questions, please. Any questions so far? Bear, are you awake? All right. He said that iPad is there, but I don't know if he's there. All right. Let's do the next example. What is that? Elimination or substitution? Elimination. So let's figure out if it's E1 or E2 now. So what do we have? We have a charged nucleophile. So if you do this, you'll be in good shape for the next exam, for the next milestone. And here you have ammonia. What kind of solvent is ammonia? Polar protic or polar aprotic? Protic, yes. Polar protic because the hydrogens are next to a heteroatom, nitrogen. All right, and so you're making an elimination. So we're eliminating one of these H's. It's gonna come out. Notice that this is a tertiary alkyl halide, so it's bad for SN2. So, but it's good for E2. All right. So here's your charged nucleophile. Grabs the H, makes the double bond, and kicks off the tosyl group. That is a tosyl attachment, tosyl group. And it makes the double bond. And it makes the scissors alkene. Oh, here's an example of the scissors alkene that is thermodynamically driven. So, not bad. All right. All right, let's do this one. What do you see? First thing that should pop to you is that your nucleophile and your solvent is one. Some books actually do this. They repeat it. Ammonia and ammonia. Meaning one is the nucleophile, the other one is the solvent, but most literature out there just writes it once. So when you have only the solvent as your nucleophile, immediately you have to say, oh, this is solvolysis. And solvolysis means what? Oh, this was E2. Solvolysis was what? SN1 or 2? 1. All right. So basically what's happening in here is that this group leaves. It simply leaves. It makes a carbocation. That carbocation could rearrange if it wants to, but it's happy there because it's tertiary. So this is a tertiary alkyl halide to start. And then the ammonia comes in attack. All right. And so you make NH3 plus, then the OTS or another ammonia grabs the proton that is there, here, and it turns it into NH2. So this is a pure SN1 substitution reaction. All right. Let's do the next one. And stop me if you have a question. All right. So over here, I forgot to write down that I have a weak. Let me find my red pen. This is a weak neutral nucleophile. And it's also a polar protic solvent. That's what the 2P stands for. All right. All right. And okay, so let's do the next example. So what does this tell you right now? What is, it's not an elimination. So it's going to be an SN. The question is 1 or 2. At first glance, by looking at this leaving group switched by this one, what do you think it is? 2. SN2, yes. Why? Because your alkyl halide is primary. And SN2s are favored by primary alkyl halides. You see that? You have to know all these little concepts and put them into play. So your sodium iodide is actually a charged nucleophile. Check that out. And the moment you see sodium there, erase that thing from the face of the earth. Because it's doing absolutely nothing and not helping you. So this is a charged nucleophile. All right. Acetone. Acetone looks like this. It's a ketone with 2 methyl groups. Is that protic or aprotic? Polar protic or polar aprotic? Aprotic. We don't have a H next to a electronegative atom, so this is polar aprotic. So it's prime time for SN2, and the iodine is polarizable. We learned that term earlier. Comes in around here and kicks this off. This is kind of like Mackenzie kicking the soccer ball right here, ready for a PK. Then she kicks it in and kicks that ball out. The tosyl group is the ball. All right, so now you have an iodine group there. Notice that these 2 hydrogens make this carbon achiral, so it's no chiral. So it's now, this is another thing that you have to watch out for literature problems. I took this from the literature. I didn't make these problems myself. Sometimes I like to challenge myself to see if I can do these things. And notice that these 2 are methyl groups, and they have them wedged and dashed. Come on. There's no need for that. That is confusing, right?
Wait,
you see that?
It should be, because if you go up, it's going to be different than the one back.
Oh, yes, you are right. You are right. Oh, ding, ding, ding. Then, thank you. Yes, so that would be, then we need the wedge and the dash. I didn't even look at the left side of the molecule. You're right. Very good. So yeah, there is chirality here. And there is chirality here. So we have double chiral. And that chirality stays. Very good. All right. So let's do the next problem. All right. All right. For number 2, we have SN1s and SN2s only. There's no E's here, no elimination reactions. All right, let's start with the first one. What do? We're going to dissect it, yeah. So the first thing is, okay, eliminate that sodium. If you see sodium or potassium, get rid of it. Put a little negative sign next to the atom that is attached to it, and then say, okay, this is a charge nucleophile. All right. Ethanol and water. Both of them are polar protics. So that's a solvent system. Is this reaction? Oh, and then this is a primary alkyl halide. This reaction is screaming what? SN what? SN2. Because we have a charged nucleophile. And this is a strong charged nucleophile. All right. So we're going to notice that nothing happened on this part of the molecule, so that keeps that skeleton intact. And here we're going to put a nitrile group. You can put a CN like that, or you can do something like this, a triple bond N. That's the same thing. So don't get tripped by that, because those two things you should know. All right, for simplicity, let's keep it at CN. And yeah, these conditions were favored for SN2. All right. What about the next one? What is this reaction telling us? So first of all, Ben, this is the kind that I don't like. This is the kind that I don't like. That's the one I don't. You notice that you have two ethyl groups there. This molecule is not chiral, and then they draw it with dashes and wedges on the methyl and the bromine. That's not necessary. This molecule could have been just written like this, and it would have been fine. You see that? All right, but they want to make it a little more stylish. So, all right, you want stylish? Let me use this stylus. All right, so what do we have here? The solvents are methanol and water. So polar protic, and they're also a weak nucleophile. Weak nucleophile. All right, so if it's a weak nucleophile, I'm dealing with a what? SN1. All right, does that make sense? Yeah, definitely not SN2. And so what will be the SN1 products here? Usually is retentional configuration, 50%, and then 50% inversion, right? But we don't have a chiral center. These two groups are just tricking us. So basically we'll have, let me change the colors. We'll have this. The first one, I'm just going to keep the configuration because it's not chiral. So this one will give me, which one of those two you think is a better nucleophile, the water or the methanol, and why?
The methanol has a lower pK than the water, so the methanol is a bit.
Exactly. By pK, you solve it by pK, really good?
16 and then 15.
16 and 15, exactly right. So the methanol is a better base. Also, the methanol has an R group, so it's electron donating. So if you want to solve it that way, you can say, oh, this is a better nuke, because bases are good when they have electron donation. Yes, sir.
Since they're so close, could you technically have 4 products? Or if there was a chiral center and then you have the inversion and
yes,
super similar.
exactly, because exactly right. You will have 4 products if you have a chiral center. But in this case, we don't have a chiral center. So how many products we will have? 2. Exactly right. So the first one will be the methoxide there. And the second one will be with the OH right there. All right, so that's SN1.
And the methoxide is the major and the alcohol is the minor.
Yeah, we can predict that. But it's not asking you to predict. But yeah, I'll probably say anywhere from 60-40 maybe. It won't be 50-50. Anywhere from 60-40 to 70-30. Quite possible. Now the other thing that we'll also, we don't know the ratio of the methanol with water, because if there's more water, the water is going to swamp the reaction more, so it could change the percentages also. All right, but we can think about all these things, and these are things that we can, analyze. All right, how about the next one? I forgot this was a tertiary. Oh, notice that this is a tertiary alkyl halide, so that favors SN1. All right. So what do we have next? We have this alkyl halide, and we have this one right here. So we have a combination of a primary and a secondary. Which one will react under these conditions when you have one equivalent of sodium iodide? The primary one, yes. So that will be your SN1 or SN2? SN2, very good. So cancel that sodium, put a negative on the iodine, and let's bring on the attack. Goes there, attacks, and kicks that one off. All right, notice that because you only have one equivalent, you only gonna have one product. Also, the acetone is polar aprotic. All right. So now you have this part of the molecule stays the same. It preserves the chirality of the chlorine there, and here we will have an iodine group. So this molecule is solely SN2. All right. How about the next one? Is that molecule chiral? No. Good. It's not chiral. It has two methyl groups. One is wedged, the other one is on the plane. But that's just optical illusion. This molecule is not chiral at all. But I think the publisher does it so that you can write down a nice final product, I think. Because the final product for this will only be one product also. We only get one product here. So let's do the analysis. Let's dissect this molecule. This reaction. So we have neutral, weak nucleophile. Temperature is room temp, 25 degrees. Over here we have a tertiary alkyl halide. So I'm going to put it like this, alkyl halides as a table. And so what we're getting here is this. I'm going to put it with a wedge, but in reality, you don't need a wedge here. You can just do like this. So that's your ethanol group attached. This reaction is SN1 or SN2? SN1, very good. It's SN1 because of the weak nucleophile, which happens to be the solvent, and the solvent is polar protic. And it's solvolysis because it only uses solvent as the nuke. So 2 in 1. All right. How am I doing time? Doing really well. All right. Number 3. Any questions? Any questions? Yes. No, you don't. You don't have to put the dash or the wedge. What the literature has is this, which baffles me. And I'm like, come on, man, these two methyls are the same thing. So it's definitely not chiral.
How did you know that it was a neutral weak nucleophile?
Oh, yeah. Who is asking?
Adia.
Adia. Oh, okay. So if you look at your solvent, it doesn't have a charge. So it's neutral. And because it doesn't have a charge, it's weak. Is that good? Oh,
Yes, thank you.
you're very welcome. All right, let's do number 3. All right, for number 3, I want you to give me now reagents to complete this. Let's start with the first one. What would you use in this situation? Check out what's happening. And also, again, the publisher is trying to trick you. Why they didn't write this like that? That would have been easier to do it like that. But they rotated this, that bond was rotated. Actually, it was this one that they rotated that so that it looks like that. You see that? Now the CN was down. When you flip it, it looks up. But it still, it came from an SN2 reaction, right? So this is an SN2 reaction. All right. And what would you use here? Help me out.
Sodium cyanide.
Sodium cyanide. And what? What solvent will you use? Huh?
Use ethanol.
Ethanol will be polar protic. Give me a polar aprotic because it's an acetone. Acetone. Very good. That's exactly what I have here on my notes. But you could use DMSO. I mean, this guy, man, you are a walking textbook, man. That's awesome. All right. And that's a compliment, man. It's not an insult. All right. So that's really cool. That's an SN2 reaction. All right, let's do the next one. What do you think that reaction is? What type of reaction is that by looking at it? From starting material to product. Yes, it's SN1. Very good. Because it's tertiary. Very good. So you have I forgot, this one was a secondary alkyl halide. This is a tertiary alkyl halide. And I'm seeing that I'm exchanging this bromine by this NH2 group. What will I need here? Only one reagent I need. The solvent and the nucleophile is the same on the SN1. What would be here? NH3. And what is NH3? Called ammonia. This is the stuff people use to clean the pools. You take a little whiff of that, it will knock you out. So when you mix ammonia with water, you make ammonium hydroxide. And that's what we're used to seeing in the lab. It's basically just liquid ammonia dissolving water. But pure ammonia, you can actually have pure ammonia. You can buy a tank of ammonia, but you need what is called a cold finger to keep it liquid, because you need to always keep it cool. If not, it evaporates. It has a very low boiling point. All right, so that's that. How about the next example? What is happening here? I'm exchanging the OH, which is a bad leaving group, with a bromine. All right, so this OH is a bad leaving group, but this is a tertiary alcohol. How can we go from left to right here? How can we make OH into a good leaving group? We have to protonate it. Exactly right. So we're going to add a proton. And what else we're going to add? No. What if you mix an acid with sodium bromide? So what do you make? Yeah, HBr. So you add hydrobromic acid. All right. So what this will do is this OH grabs this H, kicks off the bromine. Now you have water as a leaving group. And this guy just simply leaves. All right, leaves, and then it makes this flat carbocation. And then the bromine that was kicked off looks at it and says, aha, I can attack you from the top or from the bottom. But because the ethyls are the same, it doesn't make two products, it only makes one. And so that will make this top or bottom attack. It makes that. All right? And that molecule is not chiral. So this is SN1 because we form a carbocation. This is a tertiary carbocation, very stable. It likes it. All right. What about the next reaction? What are we exchanging here? A bromine for a thiol group. So what are the ingredients for the reagents? Yeah, let's put the spectator ion. My favorite, sodium. It's always there. I see him even in the soups that I eat. I love my tortillas. And for solvent, anybody can suggest a solvent other than acetone that is polar aprotic? One that you have seen so far. Let me take you through memory lane again. Yeah, my man Wise. Yeah. You're the man. Very appropriate last name, by the way. Very proud of you, man. All right. So, check out what's happening here. We're going to attack. Sodium didn't last long here written. So, put the negative sign there. Kick this guy out. It's going to flip this configuration. So, basically, when this flips, this one will flip too, because it doesn't want to be a boat, right? So you end up with what? So it's footrest, so it's going to be a headrest. So, and then it's going to be equatorial. And so you do another flip here. Just rotate this molecule like this, and that's that. You see it? Maybe not. Let me fix this. It's the same thing. So I'm gonna just flip the molecule footrest with the headrest, and now your SH will be equatorial up. All right, so this reaction is an SN2. So watch out for those rings, because you have to flip them like we flipped the chairs. All right, let's do number 4. Oh, how much time I have? 5 minutes. Man, I'm just like I was this morning. I had enough time for a couple of problems. All right, let's do the first one. Okay, so we're going to do an analysis. Analyze the reactants and reaction conditions. Then predict the structure of the major organic product. This is important, the major organic product. And indicate the predominant mechanism, SN1, SN2, E1, or E2 of each reaction. All right, so I'm going to write down here my analysis. And right here, I'm going to write the type of reaction, SN1, SN2, and so forth. And here, I'm going to write the products. There might be more than one product, and one will be a major. We have to predict the major. All right, let's do the first one. What do we have? what kind of alkyl halide. Start with the alkyl halide. Look at the substrate. That's the first thing you see. And then you say, okay, I have a primary alkyl halide. Let's represent it with an Rx. All right. Oh, there's a new thing here that is being introduced. Temperature. All right. 82 degrees. Is it considered high or low temperature? You probably don't know this answer yet. Yeah, it's kind of moderate. So anything above 60 degrees is considered high temperature. All right. So if it's 60 degrees and up, it's considered high. So 80 degrees, 82 degrees, you can touch the vessel that is heating the reaction. It probably won't burn you, but you will feel it. You immediately jerk your hand out because it's hot. It's getting hot. We know that boiling temperature of water is 100. That definitely will burn us in an instant. So 82 is considered high. So this is a high temperature. High temp. And we have a charge nucleophile or base. We don't know what's acting like. All right. So this base is potassium spectator ion T-butoxide. Most people like to draw it like this. I call it like the chicken leg, right? Other like to draw it like this, and it's fine. That looks predominant at T. That's what people think. Oh, that's T-butoxide. So people like it like that. So because I like food, I like my chicken legs. All right. So notice that we also have the solvent is. Oh, we didn't put the solvent here. Solvent is polar protic solvent. All right. All right. So what do we make here? Is this a nucleophile that can kick out the bromine based on its bulkiness? It's too bulky, exactly right. These methyls are huge, and they're not gonna be able to come in here and attack there and kick off the bromine. That's not gonna happen. So it'll be easier for it to simply deprotonate and then do elimination. So this is an E2 synthesis, and we get CH3, CH2, CH, double bond CH2. I don't like drawing condensed structures, but if you are like me, just say I make this. Make that. Linear structures better, quicker for a test too. So that then you make but 1-ene. All right. If you just give me 1 minute, we can try to solve the next one. So the analysis. Let's do the analysis on the next one. What do we have? We have a primary alkyl halide again. Primary Rx. We have high or low temperature. Low temperature is cold. Low temp is good. We have a charged nucleophile or base. We don't know yet. So right here on the top, that acted as a base instead of a nucleophile. We don't know yet what this is. And then we have another polar protic solvent. All right. So what do you think we have? Oh, the charged nucleophile. Oh, let me say high temperature, let's call this bulky charged nucleophile. And this one will be small charged nucleophile, just to make the difference. All right, so that is screaming to me SN2, very good. This is an SN2 reaction. And so the SN2 will give us what? Will give us, so this is 1, 2, 3, 4 carbons, 1, 2, 3, 4, and one more, and that will give us this CH3 group right there. All right, only one product. All right, well, let's stop here, and we're gonna continue doing this on Monday. Have a wonderful weekend, guys.